Okay, guys, in this lesson, we are going to move on from our parent function of f of x equals ab to the x, our basic exponential function, where a is the initial value, b is our common ratio or the multiplier, and we're going to move on and transform the parent function to create new versions. And just like with quadratic transformations, we're going to have a variable h, a variable a, and a variable k. And each of these transforms the parent function. We're going to use Desmos, so you're going to log on to desmos.com and go to the calculator, and we are going to use this handout that you have to explore what happens when we change the values of h, a, and k. What do these variables, how do these variables affect our parent function, y equals 2 to the x, and our exponential decay parent function, y equals 1/2 raised to the x. So we'll start with our parent functions, and then we'll transform those by changing the values of h, a, and k. So on the left side of your handout, we are going to be changing the parent function of f of x equals 2 to the x. This is our exponential growth because our b value is more than 1. So let's go ahead and write in our a value is 1. There's an understood 1 out front. That's the initial value. Our multiplier or common factor is 2. So all of our outputs are increasing times 2. And then on the right side, we're going to be taking a look at the parent function that's our exponential decay parent function and changing it up given our new variables. So in this exponential decay, our a is 1, our b is 1/2, the initial value, there should be an I right there, is 1, and our common factor is 1/2. So let's get started. We're going to write our first equation, and our h value is -6. So we're going to start out with this basic equation. I'm just going to say y equals, our a value is 1, our multiplier is 2, and then it's x minus the h value. So it's x minus -6, which becomes x plus 6. So what we're going to do is we're going to type this equation. Our parent function is going to be in cell 1 in Desmos. We're going to keep that there the entire time. And in the second cell, we're going to write our new equation. So let me share with you how you type this in Desmos. So our parent exponential growth is y equals 2. And then I'm going to use the caret, which is shift 6. And that puts my cursor as an exponent, x. So I'm going to keep this while I work on the left-hand side of the handout. And then each new problem, I will type in the second cell. So y equals, and now watch very carefully. I'm going to do shift 6. Now here's the deal. My exponent is x minus -6, which is x plus 6. I must use parentheses, so I tell the cursor that I want this entire expression to be a part of the exponent. If we don't use parentheses, it's going to put plus 6 alongside here. So you can see that whenever we have a negative h value, our parent function is now shifted 6 units left. We could take a look at where our y-intercept is here at 0, 1. And if we shifted, it is now this 0, 1 has shifted 6 units to the left. So our h value shifts horizontally. So where it says transformation, we're going to say that this parent function shifted 6 units to the left. And then you're going to complete your domain range, asymptote, growth, decay, interval of increase or decrease, and in behavior. I'm not going to go through that right now, but you can check the answer key. Now let's go ahead and do one when we change that same h value to -6, but we're going to take a look at the parent function that is a decay. So now we're going to change this, and because our base is a fraction, we must use parentheses. So I'm going to copy this. So that's our parent function. I'm going to copy that just to make it easier. Paste it. But we want to show a movement where h is -6. So again, I have to use little parentheses and say x minus -6, which is really x plus 6. And we can see, you could see that shift 6 units left. So again, our h value shifts our graph left and right horizontally. So here's our new equation. Y equals, my a is 1, my b is 1/2, and it's x minus -6. So that's our new function, and this transformed 6 units to the left. And then again, using your graph, identify these key features. So again, all the way down on the left side, our parent function is 2 to the x. Keep that in the top cell. And then you can do all the ones on the left and then come back and compare to see what happens when our parent function is a decay. When you're finished, you can check the answer key on Canvas. So let's pause the video and then I'll give a recap. Okay, a recap of this lesson. If you noticed, let's start with the h value. Our h value shifted left and right. When h is negative, it shifts left. When h is positive, it shifts right. But we have to remember what this looks like is x. So when we shift left, it's x minus a negative value, which becomes a positive. And what it looks like when it shifts right is x minus a positive value. So the h shifts left and right. Our a value affects it 2 ways. If the absolute value, again, if it's negative, we're not worrying about that. If the absolute value is more than 1, we call it a stretch. Our exponential stretches. It goes up quickly. If our a value, the absolute value, is between 0 and 1, like 1/3, 2/3, 1/2, anything between 0 and 1, we call it a compression. And it grows more gradually. It's being compressed and flattened out, where the stretch goes up quickly. Our k value, let's do one more thing. We still have the other part of a. If our a value is negative, if this is a negative value, it is reflected across the x-axis. So here's our x-axis. If it's negative, it's going to reflect. And if this was our parent function, our reflected would be going down like this. So if a is negative, it is a vertical reflection. And then the k value shifts up and down. So you can see here, when k is positive, it shifts up. When k is negative, it shifts down, and that affects your asymptote and your range. Our h value, again, it affects our parent graph, left and right, horizontal. Just think horizontal starts with h. When our a is negative, we have a vertical reflection. When the absolute value of a is more than 1, we can see this green goes up more quickly. We call that a vertical stretch. When a is between 0 and 1, like 1/2, you can see the green is going up more slowly. It is a vertical compression.